Okay, welcome to our video here on non-state diffusion. Thought we would open with an example of where we can see some diffusion changing matter in an effort to access brass, a substitutional solid solution between zinc and copper. So at left we see a copper penny that we begin with. You can see through the transformation that this copper penny is going to end up looking less coppery. It's going to look more silver-like. And I use the term silver to describe color, not actual chemical composition. We're going to see in the video here that this is going to be transformed by way of a zinc sulfate, which provides zinc 2+ ions that are dissolved in water. Okay, so I'm going to use the aqueous symbol there. And we also need the copper penny to be in contact with fresh zinc solid to allow for some electron transfer to reduce the zinc 2+ down to a metallic zinc 0 state that ends up as the film that we register with our eye as the silver layer on this copper penny. So in this kind of view here, we see what could be regarded as a pure zinc layer coating on top of a pure copper layer. The next part of the video, this gets transformed into brass, something like you might be familiar with the simple application of heat. Okay. Some additional things you might see, there's going to be a treatment of the zinc solid initially to remove the zinc oxide on it using an ethanoic acid to remove that oxide and expose that nice fresh zinc to make sure that this plating reaction occurs nicely. And then you'll see kind of a rinsing to remove excess chemicals from the first step, and then a heating on a hot plate to give us that nice brassy look. Okay, so I'm going to just play that video. You're welcome to, of course, skip this part of this video, provided you watch the YouTube video here separately. We're going to start at about 36 seconds in that video to get going. Okay.
Got my pennies to put in. Can you see it? Perfect. So let's look at the chemical equations here. The first one makes sense in IB chemistry. The second one doesn't, though. So zinc and copper touching each other in an electrolyte. The zinc has a more negative electropotential for its half cell voltage. And so what's going to happen is the zinc turns into zinc 2+ ions, and it drops 2 electrons off onto the copper. That makes sense in IB chemistry. The next bit doesn't, though. The zinc 2+ ions are attracted to the negative copper penny and then plate it in zinc. If you look at the equation, the arrow just flipped around again. So the penny is now zinc plated. So that explains the silver colour. Now, when you heat up the zinc coated penny on the hot plate, what happens is the heat gives enough energy for the metallic bonds to break. And when they break, the zinc and the copper ions start to swap places, and that gives you the yellow color of the brass. I think there's someone hoovering outside. And when that cools down, you get the color of cold brass, which is gold colored.
Okay, so that video was nice because it not only gave us an example for diffusion of zinc into copper, but it also gave us a little bit of an atomistic view as to what was happening. And so building off those ideas, I've put a little detail to that here. Prior to even applying any zinc at all, you might look at the topmost cross-section of our copper, and so you can imagine turning that on edge and looking at that. And so right here, this is going deep into the copper penny. Okay, and of course up here we've got air. And then after the zinc has been applied by way of that zinc sulfate zinc 2+ reaction with the 2 electrons within the conducting copper metal, we plate on zinc. And that is represented here now with the gray atoms that we see here. So this is the plated zinc. And below that is, of course, the copper that we had. And then emphasized through the video as well as here, we know that after some time, some heating time, that we observe diffusion and we start to form that sort of brass layer eventually, and that's what gave us the yellow coating above. So today's topic, we're going to look at a condition for non-steady state diffusion, for how zinc here could supply copper, which is a very deep material relative to the coating of zinc that we had, with zinc. Okay, and we're going to look at some conditions here. So we're going to keep some of these ideas in mind as we digest a more complicated scenario for diffusion. So we'll come back to ideas in this, and do rewind the video to these profiles for concentration if you're a bit lost. But in short, we're going to see that most of our diffusion fundamentals for non-steady state diffusion are going to try to fit these concentration profiles for zinc that I've just cartooned over here in red, where we build from no concentration deep into the copper, and we rely on that being constant for our model. And then we're going to see this sort of S-type curve. It's a Gaussian error function curve that is going to fit nicely by way of solving a partial differential. And that model is going to assume that the concentration of zinc here is always the same and not changing with time. That, as you're going to see, is a little bit of a deviation from the experiment we see in our video, where we know we may eventually run out of that zinc on the surface, and it would fully infuse into the copper. So it's simply a condition of the math is that we need to assume there's an infinite amount of zinc available at the surface to provide the diffusion of zinc into the copper.